Hi, my name is Samir Desai, and in this video I'm going to teach you how to predict the order of reagents used to protect an aldehyde or ketone.
In an earlier video, you learned about the importance of alcohols and how their reactivity allows for the synthesis of many other molecules. Also covered was the necessity for protecting groups. The reactivity of alcohols allows for the conversion to many compounds, but this also means that we'll react even at inopportune times. This is where protecting groups come in, selectively preventing the alcohol from reacting with other reagents. Similarly, there are ways to prevent functional groups, like aldehydes and ketones, from being attacked. The premise is fairly straightforward. Aldehydes and ketones contain a carbonyl group, and the more electronegative oxygen is able to pull in electrons, resulting in a high electron density at the oxygen as well as a partial negative charge. This also means that the low electron density surrounding the carbon results in a partial positive. This makes the carbonyl carbon on aldehydes and ketones particularly susceptible to nucleophilic attacks. One mechanism of protecting an aldehyde is to treat it with an alcohol and an acid, resulting in an acetal. And a ketone transformed into a ketal, which is very similar to an acetal, but with an R group in place of the hydrogen, is also a mechanism to protect the functional group. There are two types of products formed depending on the reagent. A branched ketal or acetal will form when the reagent is alcohol, while a cyclic forms when using the diol ethylene glycol. The protecting group can then easily be removed when introduced to acid and water, reverting back to an aldehyde or ketone. Let's apply all the information we've learned about redox reactions and protecting groups to the following question. The question asks us to determine the order of the four reagents listed below in order to create the final product, 3-hydroxypropanol, which contains an alcohol and an aldehyde. Taking a look at the reagents, lithium aluminum hydride in A is a reducing agent and can increase the number of bonds to hydrogen or decrease the number of bonds to oxygen. 3-oxopropanoic acid in B looks like this, which contains an acid and an aldehyde. Notice the hydroxy group and the carbon-oxygen double bond are in the same location as the end product, so this is likely the starting reactant. In order to prevent the reducing agent from converting the aldehyde into an alcohol, we want to protect it. We can treat the 3-oxopropanoic acid with an alcohol and acid. In this case, ethanol with H+, which, with two equivalents, will create an acetal containing two fairly inert ether groups. This is exactly what we want because the aldehyde is now protected. Now that the aldehyde is protected, it wouldn't make any sense to immediately remove the protecting group by using an acid and water. Rather, notice the carboxylic acid. See how it differs from the final product, which only contains an alcohol? This indicates the next step would be a reduction, using lithium aluminum hydride, which will react to produce an alcohol. Finally, the addition of acid and water in C will remove the protecting acetals to create the final product, 3-hydroxypropanol. Therefore, the order of reagents would be B, D, A, and C. Good work! This lesson required a lot of foundational knowledge of redox reactions, so definitely review previous lessons if you do need to refresh your knowledge of prior concepts. By this point, you should feel comfortable with predicting the order of reagents used to protect an aldehyde or ketone. Make sure to follow up this lesson with some practice to solidify the concepts.